Welcome back. In this video, we continue our study of Chapter 2 and we move to Section 2.2. I changed a little bit its name because the rules of differentiation will be discussed in this section and the next one. So in this section, in this video, I'm going to talk about linearity of differentiation and the chain rule. The product rule and the quotient rule will be discussed in the next section, so next video. Okay. So, in order not to repeat the same thing every time, I will use this convention. When I write f small f as a function from u, which is a subset of e into f, what do I mean by this notation? I will mean that e and f are normal spaces, and u is an open subset of e. Okay. Okay, so the first rule of differentiation is, as we expect, the fact that the derivative of a sum is the sum of the derivatives, and the derivative of a multiple of the derivative, so on. So you understand this. So if you have two differentiable functions at the point A, and we have a real constant lambda, because everything is real here. So if f and g are differentiable at a, then their sum is differentiable at a, and any multiple of f is also differentiable at a, and you have the usual expected rules. So the derivative of the sum is the sum of the derivatives. And now here, actually, we are summing not numbers in general, we are summing linear operators. Okay, because f prime of a is by definition a linear bounded map from e to f. Okay, so when I apply an increment h, then I get an element in capital F. Okay, now this is straightforward. We go back to the definition. So near h equals 0, we can approximate f by its tangent. Same thing for g, and we just add now these two. And by the rules that we explained in the beginning, small o of h plus small o of h is small o of h, in the sense that, well, small o of h is not really a number, okay, or a vector. It's really a set of maps which satisfies that the map norm over the norm of h tends to 0. So it's a set of maps, if you like. So what do I mean by that is that if I have a function, let us say r of h, which is small o of h, or r1 of h, and another function r2 of h, when I add the two, I get that the sum is small o of h. That's what I mean. So this is a very convenient notation. Now, if you don't like this, to use this notation, you can go back to the epsilon delta definition. Okay, so same thing. So when we add these two, we get that f plus g evaluated at this a plus h minus f plus g evaluated at a minus the sum of the derivatives is small o of h, and this is now linear unbounded. So this, by definition, means that f plus g is differentiable at a, and its derivative is given by this term. Okay, and same thing for lambda. When I multiply by a constant, a small o of h remains a small o of h, as you may check, and therefore this identity or this condition means that f is differentiable at a, lambda f is differentiable at a, and its derivative is lambda times the derivative of f prime at h. Okay, so pretty straightforward. Now, if you don't like this notation, you can use the big D notation for derivative. So Fréchet derivative of f plus g at a is the sum of the derivative. So if you like this, if you encounter this somewhere else, don't panic, because we can use different notations. Okay. Now, and so a corollary of this is that the sum of two C1 functions and the multiple of a C1 function is also C1. Why? So we already proved different. So the sum of two differentiable functions is differentiable, we know that. Now, if in addition the derivatives are continuous with respect to the argument, the derivative of the sum is the sum of two continuous functions, so it's continuous. Okay, and this is a property of that we studied in topology. Whenever it's defined, the sum of two continuous functions is continuous, and the multiple of a continuous function is continuous. So, okay. Next result is the chain rule. So we have two functions, f and g, but note that they are not defined on the same set. Okay, so f is a function from an open subset of a normal space into another normal space. And G, notice that its domain of definition is a subset of the target space of F. Why do I need that? Because I need to compose G by F, G circle F. So I first go from E to F by small f, and then I go from F to another space, G, by composing by G. So always pay attention to, so I need, now I assume that in order for G circle F to be defined, I need that the range of F be included in the domain of G. So I assume that small f of u is contained in capital V. Okay, so we can draw a diagram from E to F and from F to G. So as we expect, if f is differentiable at the point A in the domain, and G is differentiable at the image under F, so it's differential at f of A. Okay, then the composition, which is well defined, is differentiable at A, and it's given by this formula. So the derivative of the composed map is what? Is the composition of the derivative of G evaluated at f of A or at B, composed with the derivatives. Now here we are not, in general, these are not numbers, these are linear maps, linear bounded maps. So I'm composing linear bounded maps. Okay, so if you want to get a vector in, let us say, in G, you have to evaluate this at H, and then you'll get G prime f of A evaluated at f prime of A evaluated at H. Okay, so this is the difference between the real case that you know. In the usual chain rule in calculus, you just have to multiply. Why? Because we identify real numbers with linear maps. Okay. So now we will see where this formula comes from. So, or if you like to use the big D notation, same thing. Okay. So capital D of G of F at A is the composition of these two derivatives. Okay. So why is that? We go back to the definition. So first we write the differentiability condition at A of F, and we'd better write the remainder here as phi of H, where phi of H is a function which is small o of H. So the norm of phi H over the norm of H tends to 0. Or if you like, norm of phi H less than epsilon norm H for H less than some delta. And we shall go back to this. Okay, so this is just the differentiability condition of f at A. And now we write similarly the differentiability of G at B, which is the image under f of A. So we write it in this way, but in a slightly different way. So instead of taking an increment h, I take the increment to be y minus b, but it's exactly the same thing. So instead of writing g of b plus k, I write g of y. Now you will see why, but it's completely equivalent, as you know. Okay, and the remainder is a small o of the difference of the increment. Okay, so slightly different. You will see why I wrote it in a slightly different way, but equivalent. So this is condition 1, differentiability of f at A, and this is differentiability of G at B. Okay, so I will refer to these two equations now. Okay, now if in equation 2 we replace y by f plus h and b by its value actually, so b equal f of A, so equation 2 becomes G of evaluated at f of A plus H minus G of FA is the derivative, as we know, evaluated at B, which is f of A, times the or evaluated also because this is an increment here. Okay, so it's important to understand the meaning of where each term lives. Okay, so these two terms live in capital G, in the target space of small g. This is a linear bounded operator, and this is the argument of it. So this is actually in capital F. This is a linear map from capital F to capital G, so the result is in capital G, okay, plus the remainder. Okay, so now we use equation 1. So we replace the difference between f of a plus h and f of a by its value, which is f prime by equation 1. So we use equation 1. We put equation 1 in this equation, right? So we get g of f at a plus h minus g of f at a equal g prime of fa, which is a linear bound operator, evaluated at this vector, plus psi, same thing. So I didn't change, so nothing mysterious. And now I use linearity of g prime of fa, okay, because this is really a linear bounded operator, okay? So linearity tells me that this is the sum of g prime fa evaluated at this plus g prime fa evaluated at phi of h. So I split it into two terms. And now I just rewrite this linear term in h actually can be written as g prime of fa composed with f prime of a, everything evaluated at h. So this is precise. These two terms are exactly the same. This one and this one are exactly the same. Okay, and so that's it. So we see that here this is linear, and of course it's bounded. Why? Because it's a composition of two continuous functions. So this term as a function of h is linear and bounded. Okay, so g of f evaluated at h plus h minus g of f evaluated at a minus this linear bounded term will be equal to the sum of these two. So in order to prove that g of f is differentiable and its derivative is given by this term, we have just to prove that the sum of these two terms is a small o of h. Okay, so just definition. Okay, now, so it's enough to prove that each term is a small o of h, right? Near h equals 0, of course. Now, the first term is not difficult because you can just go back to the definition. If we evaluate the norm of this quantity and we divide it by the norm of h. Now, since this is a linear bounded map, the norm of its value at phi of h is less than the norm of the operator and the operator norm times the norm of the argument, which is phi of h. Now, this is just a constant, actually. It doesn't depend on h. The norm of g prime fa is just a constant. And by assumption, phi of h is a small o of h, so the norm of phi h over the norm of h tends to 0. So when I multiply by a constant, the result tends to 0. So this term is now a small o of h. So we'll just focus on the second term. Okay. So here I need to go back to the definition. So let epsilon be given and consider the constant defined by the norm of f prime a, the operator norm of f prime a, plus 1. Now you'll see where this constant comes from. And now I go back to the definition. The remainder in equation 2 was psi of y, which was a small o of y of minus y minus b. So by definition, given epsilon, we can find a number delta positive, such that the norm of phi y is less than epsilon times the norm of y minus b whenever the increment is less than delta. So this is the definition of small o of y minus b. Or if you like, the ratio is less than epsilon. Or the ratio tends to 0. Everything. So this, I call this equation condition 3. And now, again, I just need a particular case. We know that the remainder in equation 1 was phi of h, which was a small o of h. So in particular, if I take epsilon equal 1, I can find a number delta 1 such that phi of h in norm over norm of h is less than 1 because it tends to 0. So I don't need more than this, just constant. So take epsilon equal 1 in the condition. Okay. So phi of h in norm in particular will be less than the norm of h for h, norm of h less than some constant delta 1. Okay. And now if I go back to equation 1, which was just the condition of differentiability of f at a, and take the norm of each side. So the left-hand side was just f of a plus h minus f of a, and the right-hand side was f prime a evaluated at h plus phi of h. So I used the triangle inequality. the norm of the sum is less than the sum of the norms, and then I use the operator norm of f prime, as you know, and I get norm of f prime a times norm of h plus norm of h. So I factor by norm of h, and I get just norm of f prime a plus 1, which is the constant m. Okay, provided, of course, that h is less than delta 1. And now, last step, I take delta 2 to be the smallest among delta 1 and delta over m. You will see why, where this comes from. And I consider an arbitrary increment whose norm is less than delta 2. What happens? Then the norm of h is both less than delta 1 and less than delta over m, or equal, doesn't matter. If norm of h is less than delta over m, then norm of h times delta is less than m, or m of. And therefore, if we go back to equation 4, what do I have? M norm of h is less than delta. So this increment in f is less than delta. And therefore, I can apply equation 3. So psi of the difference, psi of f of a plus h, psi of y. So I just replace y by f of a plus h. Since the difference is less than delta in norm, then I can apply equation inequality 3. Okay, and I get that the remainder, psi of f, the second remainder that I need to prove is a small o of h. So it's less than epsilon times the norm of this increment. And now I apply for equation 4 again. So this increment itself is less than mh. So I get epsilon m norm of h. And that's it. So since epsilon was arbitrary, this precisely means that psi of fa plus h, which was the second remainder, is a small o of h. Now, we got here epsilon m, but this is not, as you know, it's not a big deal, because since epsilon is arbitrary, this is precisely what we want to prove. If you want to get exactly epsilon, then you should have taken here epsilon over m. Okay, so, but this is not important. We know that. So if you obtain less than epsilon or 100 epsilon, it's the same thing. If epsilon is arbitrary, but provided the m does not depend on epsilon. M is a constant. So that's it. So the second remainder is a small o of h, and therefore we are done. So this concludes the proof of the chain rule, and concludes, so as a corollary, composition of two C1 maps is a C1 map as well, okay? Because, as you know, the composition of two continuous map is continuous. Okay? So this is just an easy corollary. So this concludes this video, and I'm going to talk about the remaining rules of differentiation in the next video. So thank you for your attention.